So hello everyone, this is Dr. Nimish Kumar Srivastava, Assistant Professor in AKGEC Engineering College. In this module of lecture series for the optical communication, that is KEC 058, we are discussing about the various units, and in that we have covered the optical, what is the basic concept of optical in the unit first and the phenomena associated with that. Apart from that, in the second unit we have discussed the various that the signal degradations phenomena that is responsible for the degradation of the signals. In that we have discussed various dispersions, attenuations, types of dispersions and the types of attenuations. In the unit 3 we have discussed the what are the different sources that are there in optical fiber, that is LED as well as the laser, and in the last class we have discussed about the LED. That means what is LED, what is the phenomena which is responsible for the generation of a light in LED, light emitting diodes, and we have discussed the types of LEDs, that is configurations, different configurations of the LED, that is your surface emitting as well as edge emitting LEDs. And we have discussed what are the various requirements, that or what are the various criteria based upon which we can say that a particular source, that means LED or laser, is a good laser source. Means that it should be compatible with different fibers, as well as it should efficiently couple the light into the fibers. So we have discussed all those criterias, and now in this today's lecture we are going to discuss about the laser. What is laser, what is the phenomena, what is the combinations of phenomena which together they are combined, they give you a light output, highly coherent light output as well as the directional light output, and that comes under the source which is known as a laser, that is a light emitting light amplification by stimulated emission of radiations, and we will discuss its type. So first thing is that what are the basic phenomena that is occurring inside the laser, as well as what is the basic phenomena that is associated with the photons. So very first phenomena which we have already discussed in our last class about the absorptions, that whenever a charge carrier, that is electron, is present in the valence band, we know that it's in the thermal equilibriums most of the charge is present in the valence band, and whenever we are incidenting a photon on the electron, then the electron will gain the energy of the photon, and that the energy of photon should be equal to or greater than the band gap difference, that means equal to or greater than the difference E2 minus E1. So if that energy of photon is equal to or greater than the band gap of the material, then the electron will excite from the valence band to the upper band, valence band to the conduction band, and such process is known as a absorption. That means a photon absorption, that is the first thing, that is a photon absorption. Then other thing is about the spontaneous emission. So in a spontaneous emission, what is happening, whenever the electron is already residing in the higher energy level, that means in the E2. So when they are in the higher energy levels, and after their lifetime, carrier lifetime, they will again try to come back, or they will again come back to its stable state, which is the ground level, that means at the E1. So while moving from a higher energy level to a lower energy level, that will emit a photon. That photon will have an energy equal to the band gap of that material. So that means it's whatever the photon that is emitting is having an energy of h nu 12. 12 is basically the transition from a one state to the another state. Now apart from this, this is the spontaneous emission, the phenomena which is basically responsible for LED, right? Apart from that, the third one, the phenomena which is mainly responsible for the stimulated emission. That means whenever in the spontaneous emission we have seen that something which is occurring naturally, we are not incidenting some photon, we are not forcing the electron to move from a higher energy level to a lower energy level. But in the case somehow, if suppose that we are incidenting a photon, we are striking a photon, forcing the electron to move from the higher energy level to a lower energy level, then that phenomena is called as a stimulated emission, because we are stimulating the electron to move from a higher energy level, which is the unstable, to its stable state, that is towards the ground level. So that is the valence band. So electron, while moving from the conduction band towards the valence band, they will emit photons which is equal to the band gap energy of that materials, and that photon which has been emitted, they are in phase with respect to the photon which is responsible for its emission. So that is h nu 12. So emitted photon and the photon which is incidenting on the material, they are in phase. So these two photon, when they added up, like if we are making a structure in which if we have provided on the both the end of a material two mirrors, then while this photon is emitting, they will strike one end of the one face of that mirror, again move back, and this photon which have been moved back to the material, they will again strike the electron, they will, and they, as a result of that, they will emit more photons. So that means two photons that may have been emitted initially when they are hitting the one mirror, so they are giving a positive feedback, and two photon results in the emission of 4 photon. So as a result, this is a cumulative process. That means the photons is adding up, and the result is that there will be a huge number of photons that will move out of this laser. So that is called as a stimulated emissions. So we will see how we are making a provisions. We are making some adjustment in the structure of the materials, and that adjustment will leads to a cumulative process, which is which results in the adding up of the photons, and that's why we say that the laser is having a highly directional as well as a high power with respect to the LEDs. Next thing is that what are the main phenomena which together form the operating principle of the laser. In the previous one, the better word as here mentioned that the three main phenomena or three main process for a laser action. It would be better that three main process that is occurring in a source, right? It's not restricted to a laser, because laser the three main phenomena that is occurring inside the laser, these are not the three main phenomena. The better word will be a three main process that is occurring in a photonics, right? So better word will be a photonics. Now the next is what is the main process that is occurring inside the laser. So the first process that is occurring inside a laser, first and the foremost important criteria for a lasing action to take place is population inversion. Initially we have in the thermal equilibrium we have seen that most of the electron is present in the valence band, and somehow we have to make the provision that the electron which is initially present in valence band, somehow that the majority which is in the valence band, that majority moves to a conduction band, right? If that majority moves to a conduction band, only then we could have a maximum number of photons that will be emitted. Why? Because of the incident photon that is incidenting on the electron present in the conduction band, that is occurring in the stimulated emissions. So somehow we are making a provision so that most of the electron is already residing in the conduction band. So that is something process which is done by a population inversion. We are pumping, we are providing some extra energy to the electron which is present in the valence band, most of the electron which is present in the valence band. So by gaining that pumped energy, they will move to a conduction band, and if they are if they are already moved in the conduction band, now this complete process is called as a population inversion. Why it is called as an inversion, population inversion? Because we know that in the thermal equilibrium, most of the population of electron is present in the valence band, but by the provision of providing an extra energy, pumped energy, we are not reversing the population of electrons. Now most of the electron will reside in the conduction band. That's why it is called as a population inversion. This is the first process which is occurring inside the first process which is responsible for the lasing action, right? So this is the first process. First process is your population inversion. So how it is done? It is done by injecting electrons into the material to fill the lower energy state of the conduction band. Now A better figure could be like if we are having a electron, and if the electron has moved from a valence band to a conduction band. So this is electron and this is valency, this is vacancy of electron, which is called as a hole. So we are providing an extra energy to a extra energy to the carrier so that it move from a valence band towards the conduction band. So this is something, this is your valence band and this is your conduction band. So this is how a population inversion is taking place inside the laser or inside a material which is used for emitting a photon. In the previous class we have understood which material is used, that is a direct band gap semiconductors, which are used in the which are used as a material for the optical sources. Now the next thing, before that, the thing is that the first process we have discussed, that is the population inversion. The second process will be stimulated emission. And finally the last process will be optical or a positive feedback. Now these are the three processes that is responsible for a lasing action to take place. First process is reverse the population of an electron. How you can reverse the population? By injecting a more number of power, more number of energy to the electron which is already residing in the valence band, and you are now inverting the population of an electron. Now electron will most of the electron will reside in the conduction band. Now this is the first criteria. The second process is the stimulated emissions. How is stimulated emission going to take place? As most of the most of the electron is present in the conduction band. So whenever you are hitting an electron with a photon of energy which is exactly equal to the band gap of that material, and now if that photon is striking the electron will try to move to its stable state, that means to a ground state, in which we are already having a holes, vacancy of electrons. So when they move and recombine with the holes, they will emit a photons, and that emitted photon will be in phase with the photon which is responsible for its emission. So this is your stimulated emission, second process which is responsible for lasing action to take place. Now the third and the final process is called as a positive feedback. Now in a positive feedback, I have already told you that if there is a laser, a cavity, that means a length of the materials, and at both the ends you are providing a mirror, at both the facets you are having a mirror. So whenever a photon is emitted because of the help of a stimulated emission, suppose that we have got the two photons from that materials. Now when this emitted photon strike the one face of the mirror, they will be reflected back, and when they are reflecting back to the material, they will strike the electron. These electron will again generates suppose that these two photon again strike the two electrons, so these two electrons will again generate the four photons. Now in this way, this four photon again reflect back from the second end, and they will add up to the generation of 8 photons. So this is the entire process is the cumulative process, right? They will add on to the generation of the photons, and in this way a very huge number of photons will be emitted from the laser. So in this way laser is working. This is the basic, all the process, three important process that is in together they is responsible for the lasing action to take place. The next thing is that what are the different types of lasers. Once you have got the basic foundation of what are the different what is the lasing action, how they let that lasing action take place, next important thing is that what are the different types of lasers that is possible. So the very first, there is a basic laser which is your Fabry-Perot laser. Now what is happening in a Fabry-Perot laser is that we are having a two parallel mirrors, reflecting mirrors. That two parallel reflecting surfaces defines a Fabry-Perot resonator cavity, right? So what is happening here? We have used two flat partially reflecting mirrors, and they are directed towards each other. These two mirrors are directed towards each other in order to enclose the Fabry-Perot resonator cavity, right? The mirror and the facets of these mirror are constructed by making two parallel clefts along natural cleavage planes of a semiconductor crystals. Now the purpose of the mirror, what is the purpose? Purpose is to establish a strong optical feedback in the longitudinal directional, right? To establish a strong positive feedback in the longitudinal direction, because this is because of this positive feedback that we are generating a huge number of photons from the laser. Now the thing is, we have somehow we have provided a positive feedback. Now this feedback mechanism will converts the device into an oscillator, right? It will convert a device into oscillator with a gain mechanism that can compensate for the optical losses in the cavity at certain resonant optical frequencies. That will compensate for the optical losses at a certain optical frequencies. Now the side of the cavity are simply formed by the roughing the edges of the device to reduce unwanted emission in the lateral directions. Now as the light reflect back and forth within the Fabry-Perot cavity, so because of this forth and that is the back and forth reflections of a light, the electric field of the light will interfere on a successive round trips, right? These successive round trips going to interfere with each other, and those wavelength that are integer multiple of the cavity length will interfere constructively. Those wavelength which are a integer multiple of the cavity length, they will interfere constructively, so that they will add up and they will form some standing wave patterns. So all the others wavelength going to interfere destructively and thus will cancel out each other, means that they are not going to form some standing wave patterns, right? So only those wavelength going to only those photons going to form a standing wave patterns whose wavelength are a integer multiple of the cavity length. If they are not the integer multiple of a cavity length, so all those wavelength, they are going to interfere destructively and they will cancel out with each other. So they are not going to form any wave, right? Now what is happening? So the optical frequencies at which a constructive interference occurs are called as the resonant frequency of that cavity. Okay, so that is called as a resonant frequency of the cavity. As a result, spontaneously emitted photons that have wavelength at these resonant frequency will reinforce themselves after multiple trips through the cavity, so that their optical fields become very strong. Now the resonant wavelength are called as a longitudinal mode of the cavity, because they resonate along the length of the cavity. So this is the basic principle of the Fabry-Perot. Now this is the graph which is drawn between the relative wavelength as well as the light intensity inside the Fabry-Perot cavity. Now what is showing? It is giving the basic idea. It is giving the behavior of the resonant wavelength for three different values of mirror reflectivities. We have three different values of reflectivities: 0.4, 0.7 and 0.9. So now we are plotting the graph between the relative wavelength as well as the light intensity inside the Fabry-Perot laser by considering the three different reflectivities, and we just conclude that it gives the relative wavelength, relative intensity as a function of the wavelength, right? So the width of the resonance depends on the value of the reflectivity. So if you observe that higher the value of the reflectivity, that means resonance becomes sharper as the reflectivity is increasing. So the moment we are moving from a low reflectivity to a higher reflectivity, there will be an increase in the sharpness of the graph. That means graph which is drawn between, that means relative wavelength as a function of your, or a relative intensity as a function of your wavelength. So the graph between the intensity and the wavelength is going to sharpen when we are increasing the reflectivity of the mirror, which is the basic structure responsible for the Fabry-Perot lasing action to take place. Now the next thing is about the distributed feedback. So now once we got the basic information about the Fabry-Perot filter, Fabry-Perot laser, so after building this concept, we are going to discuss about the next laser, which is called as a distributed feedback laser. So we will discuss that, all those things in our next class. So thank you all. We will meet in our next class and we will start with the distributed feedback laser.